They didn't see it at first. To most of Earth, that night in mid-2025 was ordinary. Streetlights humming, phones glowing, people scrolling past headlines they'd already forgotten. But high above the deserts of Chile, one of NASA's Atlas survey telescopes stared into a crowded field of stars, taking images in quiet, relentless rhythm. Each exposure captured thousands of pinpoints, almost all of them fixed, ancient, indifferent. And in the middle of that sea, one tiny speck refused to stay still. At first, it was barely a rumor in the data, a fraction of a pixel nudging itself from one frame to the next. The software flagged it, the night operator frowned, zoomed in, checked for glitches, checked again. In one image, the speck was here. In the next, it had shifted, just enough to whisper that it was close, moving, real. He pulled the last hour of frames together, blinked them in sequence, and watched that tiny point of light carve a clean, diagonal line through the starfield, like a scalpel slicing across the sky. Protocol kicked in. The coordinates and brightness were logged, the motion vector calculated, and within hours observatories around the world were listening to the same quiet alarm. The Minor Planet Center received the report on July 1, 2025, a faint, fast-moving object coming in from the dark. For a few tense hours it sat on the near-Earth object confirmation page, a possible threat, until more data settled everyone's pulse. The newcomer was passing through, not barreling toward us. To the astronomers following its trail, it was just another mystery rock at first, one more icy fragment from the outer reaches of our own solar system. But the numbers they started to pull from its orbit didn't behave like the others. The more they refined the trajectory, the stranger it became. The path wasn't an ellipse, not even a stretched-out one. It was open, untethered, a curve that never looped back. A hyperbola. This object was not bound to the sun at all. It hadn't fallen from our Oort cloud. It was diving in from somewhere beyond everything we call home, and once it left, it would never return. That was the first twist. What had looked like just another comet candidate suddenly joined an exclusive club. After 1I/Oumuamua in 2017 and 2I/Borisov in 2019, this was only the third confirmed interstellar visitor ever seen cutting through our solar system. The label came quickly, 3I/Atlas, 3I for third interstellar, Atlas for the survey that found it. Telescopes turned toward it like eyes, snapping to a new movement at the edge of vision. At first, 3I Atlas was maddeningly faint, a dim 18th magnitude smudge buried near the dense starfields close to the Milky Way's center. But bigger instruments with longer exposures began to tease out its personality. On early July nights, astronomers saw a slight fuzziness around the core, then a hint of elongation, like a teardrop smeared across the sky. By the time Hubble caught it on July 21, the picture was clear. There was a solid, icy nucleus cloaked in a glowing cocoon of dust. 3I Atlas wasn't just a rock, it was active. It was a comet. On paper, that made things simple. An interstellar comet, a wandering iceberg from a distant star system, warming and venting gases as it plunged toward our sun. The textbooks could handle that. Its orbit, too, obeyed the rules. The numbers said 3I Atlas had come in from far beyond the sun's influence and would leave again on a clean escape trajectory, never to be captured. NASA's fact sheets marked it down as a harmless passerby, never coming closer than about 1.8 astronomical units from Earth, roughly 270 million kilometers safely distant. Still, there was something about it that wouldn't let observers relax. Part of it was timing. We had only just begun to understand Oumuamua's bizarre, cigar-like shape and non-gravitational acceleration, and 2I/Borisov's almost comfortingly normal comet behavior. 3I Atlas arrived carrying the weight of both stories, one that had fueled talk of alien probes and one that had soothed nerves with familiar physics. Scientists wanted to know, which pattern would this new visitor follow? As July turned to August, 3I Atlas brightened, slipping through the constellations Ophiuchus, Scorpius, and Libra like a ghost nobody on the street could see. To the human eye, even under the darkest skies, it was invisible, nothing more than numbers and pixels. But in those pixels, its coma grew redder, dustier, more alive, hinting at complex chemistry on its icy skin. For a while, the story seemed settled, a perfect interstellar comet. It had a fuzzy coma, a faint tail, and a color that fit neatly alongside 2I/Borisov. The outgassing looked textbook. Papers began using phrases like typical cometary activity, and news articles described it with words like quiet and subtle. If you were just reading the headlines, 3I Atlas looked like the most well-behaved interstellar visitor we could have asked for. But space doesn't care about our headlines. It cares about energy, gravity, and time. As 3I Atlas curved deeper into the inner solar system, charts of its projected path showed a dangerous-looking dip past the orbits of Mars and then inward toward the Sun. No physical danger to us, but a trial by fire for the comet itself. Perihelion, its closest approach to the Sun, would come on October 29, 2025. That was where things often went wrong for comets. Astronomers had seen it before. Bright comets threaded too close to the sun and never came out the other side, torn apart by tidal forces or cooked into clouds of dust. Even some interstellar candidates were expected to be fragile, their ice lattices hammered by eons of cosmic rays between the stars. If anything, 3I Atlas should have been weaker, more brittle, less prepared for that kind of heat. So the community braced for the second twist. Some predicted the comet would fracture dramatically, its nucleus splitting into smaller shards that would briefly flare and then fade. Others expected the coma to swell and then thin, like a soap bubble bursting under a heat lamp. Both possibilities would have been normal. Both would have explained 3I Atlas in comfortable, familiar terms, a fragile relic, beautiful and doomed. As it neared the far side of the sun, the object disappeared from our view, lost in the glare. Spacecraft took over where Earthbound telescopes could not, watching in wavelengths the human eye would never see. They tracked temperature, gas release, subtle shifts in motion. For several weeks, 3I Atlas became a question mark drawn directly behind the sun, out of sight but not out of mind. When it finally re-emerged, slipping back into the pre-dawn sky in early November, the first new images came with a sense of relief, and then confusion. There it was, still a bright central coma, still a defined nucleus, still an elegant tail sweeping away from the sun like a silver brushstroke. Amateurs and professionals alike snapped fresh exposures and stacked them, expecting to find evidence of a broken core, a cluster of fragments, or some ragged sign of catastrophic loss. Instead, 3I Atlas looked whole. Not untouched, its tail was more complex now, with plumes and possible antitails weaving through the faint ion stream. But structurally, the comet had survived its close swing around the star that unmade so many of its cousins. Where others had shattered into dim echoes, this interstellar visitor seemed almost defiant, carrying its nucleus intact back out toward the dark. That resilience did not go unnoticed. For some researchers, it was just another data point in the wide range of comet behavior, a reminder that nature is messy and that distant star systems could produce all kinds of ice and rock mixtures, some tougher than others. For others, though, the survival of 3I Atlas triggered a quieter, more unsettling thought. If an object plunges toward a star, shrugs off the heat, and keeps going with its structure strangely stable, what exactly are we looking at? The question deepened as teams began to analyze the shape and motion of its evolving tail. Some calculations suggested that the amount of gas and dust being shed was higher than sunlight alone should reasonably drive, unless the surface area of the nucleus was larger than it appeared, or unless something about its internal structure was different from what standard comet models assumed. A few voices, already tuned to the oddities of Oumuamua, wondered aloud whether 3I Atlas might not be purely natural after all. Most scientists pushed back on that idea, pointing to the clear signs of sublimating ice, the hydroxyl radicals detected by radio telescopes, the strong match with known comet chemistry. Yet the fact remained, this was no fragile snowball coming apart at the seams. It was a survivor, an object that had dived toward our star and emerged bearing scars we didn't yet fully understand. And so the story that had begun as a routine comet watch had quietly transformed. 3I Atlas was no longer just another icy wanderer. It was a test case, a challenge, a riddle dropped into our sky from another star system. The perfect interstellar comet had survived the sun against the odds, and with every new observation, the line between simple explanation and deeper mystery grew just a little thinner. By the time 3I Atlas emerged from behind the sun, everyone expected the headline to be simple. It survived. But survival was only the beginning. When astronomers pointed their most sensitive instruments at the returning interstellar visitor, they weren't just asking, "Is it still there?" They were asking, "What is it doing now?" They watched its coma, the glowing cloud of dust and gas, shift and breathe like a living thing. Within that cloud, faint structures began to appear, narrow beams, bright plumes, subtle fans of material streaming away from the nucleus. These were the jets, the exhaust of an object being slowly cooked by sunlight. At first glance, nothing strange. Comets have jets all the time. As ice on their surface warms, trapped gases escape through cracks and vents, spraying dust into space like geysers. Those jets push gently on the nucleus, nudging its trajectory in ways that careful observers can measure. For decades, scientists have used these tiny thrusts to learn how active a comet is, how fast it spins, how its surface is arranged. But with 3I Atlas, the numbers refused to sit comfortably in their usual boxes. The first models assumed a fairly ordinary nucleus, a lumpy rotating block of ice and rock a kilometer or two across, venting most strongly near its sunlit face. If that were true, the pattern of jets and the resulting non-gravitational acceleration, the tiny push from all that outgassing, should follow a predictable curve. The timing of brightening, the tilt of the jets, the way the coma thickened and thinned with distance from the sun, all of that could be mapped onto a neat, if complex, equation. But when teams fit those equations to the latest data, they found themselves making more and more exceptions. To match the observed brightness, the outgassing had to be stronger than they expected. To match the direction of the jets, the spin axis had to sit at odd angles that only barely explained the observed features. And to match the subtle changes in the object's motion, they had to assume that some jets turned on and off in ways that didn't quite fit the usual thermal story of ice simply heating and cooling. Individually, each mismatch was small. A little extra energy here, a slightly awkward angle there, a burst of activity starting sooner or lasting longer than a standard model would predict. None of it amounted to a smoking gun, but together these details formed a pattern that some astronomers found difficult to ignore. In quiet meetings and cautious preprints, a few voices began to ask the question out loud. What if our assumption that this is just a normal comet from another star system is wrong? They pointed to how evenly 3I Atlas seemed to hold itself together under stress, how coherent its jets remained after perihelion, and how the energy budget of those jets looked inflated compared to what sunlight alone should supply over its exposed surface area. If they tweaked the models to make it all fit, they found themselves painting a nucleus that was either strangely shaped, strangely active, or covered in vents arranged in improbably convenient ways. The majority of researchers pushed back. Comets are notoriously tricky. Their cores are hidden inside bright comas, and our entire dataset of interstellar examples is so far just 3 objects. If 3I Atlas looked odd, they argued maybe that was the point. Other star systems can produce weird comets. We might simply be seeing the variety of the galaxy, not the fingerprint of something artificial. Still, those jets, those lines of gas and dust carving out patterns in the coma, became the first major exhibit in a new debate. Why did some astronomers think 3I Atlas might not be a comet in the ordinary sense? Because its behavior kept drifting away from the simplest explanations. And then as that argument simmered, another piece of evidence arrived, not as light, but as a whisper in radio waves. Across the world, radio telescopes turned their metal dishes toward 3I Atlas, not to see its shape, but to hear its chemistry. When sunlight hits water ice on a comet, it liberates water molecules, which can then be broken apart by ultraviolet radiation from the sun. One of the fragments created in that process is the hydroxyl radical, OH. This fragile molecule emits radio waves at very specific frequencies, like a tiny tag shouting, "Water was here." Detecting OH has long been one of the clearest ways to prove that a fuzzy object in the sky is a true, icy comet rather than a dry asteroid. For decades, astronomers have listened for that signature from comets inside our own solar system, but no one had ever clearly heard it from an interstellar visitor before. When 3I Atlas swung around the sun and brightened, that changed. Arrays like Meerkat in South Africa and other powerful radio instruments locked onto the region of sky where the comet's coma spread. They integrated for hours, gathering the faintest signals, subtracting background noise, stacking and cross-checking until slowly a pattern began to rise above the static. A line appeared in the data, subtle but consistent. It matched the frequency expected from hydroxyl radicals created when water molecules, once frozen in deep space, were broken apart by the sun. For the first time, humanity was hearing a clear chemical voice from an interstellar comet, the radio whisper of water that did not form around our star. For many scientists, that moment was deeply satisfying. It fit beautifully with the picture they already had: 3I Atlas as a natural comet, an icy shard from another system now behaving much like the comets we've studied for decades. Faint though it was, the OH signal was exactly what you would expect from a rugged, outgassing nucleus transiting a sunlit corridor. The detection helped pin down how much water it was shedding, how active it was, and how its coma was evolving over time. But for skeptics, the radio result did something more complicated. On the surface, it seemed to close the case. Of course, it's a comet, look at the water. Beneath that surface, though, questions remained. If the jet's energy and timing were odd and yet the chemistry looked standard, what did that say about the object's structure? Could an engineered relic, if such a thing existed, be sheathed in ice or dust that mimicked a natural comet when heated? Could a shell of frozen volatiles cloak something more rigid, more deliberate at the core? Most mainstream researchers saw little need for such speculation. The simplest explanation held: water ice plus sunlight equals OH emission, plus jets plus coma, exactly as expected. Yet even some of them admitted that there was something almost too cinematic about the moment. The first clear radio voice from an object born under another star, arriving just when the debate over its nature had begun to sharpen. In that contrast, the story of 3I Atlas grew richer. On one side stood those who saw the radio detection as confirmation. This was a natural wanderer, nothing more. On the other stood those who argued that confirmation of one property, its icy outer layers, did not automatically settle deeper questions about its interior and its origin. The same data, viewed through different lenses, seemed to support both comfort and doubt. And that set the stage for the core conflict behind your title. Because beneath all the charts, spectra, and orbital solutions, a larger, more unsettling question was forming. Was 3I Atlas just a rugged piece of frozen chaos? Or was it, in some sense we did not yet understand, designed? Most researchers held the line on the first answer. They pictured a world circling another star long ago, a vast disk of rock and ice swirling at its edges. In that far-off system, gravitational tugs between giant planets and smaller bodies would have scattered countless icy fragments into deep space. 3I Atlas in this view was simply one of those fragments, a comet thrown out billions of years ago, wandering between the stars until random chance sent it threading through our solar system. In that story, its survival around the sun, its jets, and its radio whisper all spoke of endurance, not intention. It was a survivor because nature sometimes builds strong things. Its jets were complex because real surfaces are messy. Its radio signal was poetic only because humans are very good at hearing meaning in noise. But a smaller, louder group saw something else in the same data. They pointed to the odds, 3 interstellar visitors in less than a decade after centuries of silence. They pointed to Oumuamua's strange acceleration and geometry, to 3I Atlas's unusual resilience and jet behavior. They asked whether our era of deeper, more sensitive surveys was merely revealing what was always there, or whether we were witnessing the arrival of specific messengers from the wider galaxy. In their eyes, the survival of 3I Atlas around the sun wasn't just a testament to strong ice. It looked like rugged engineering. The jets that didn't quite line up with standard models weren't just statistical noise, they hinted at a more controlled or structured source of thrust. The radio whisper of broken water molecules wasn't just chemistry, it was a clever camouflage for something that, at its core, might not be a simple snow and stone ball at all. Most of the scientific community disagreed, but disagreement didn't make the questions go away. Instead, 3I Atlas became a kind of screen onto which humanity projected its deepest curiosity about the universe. One group saw a natural ice ball telling us that planetary systems like ours are common, that comets from other stars roam the galaxy by the trillion. Another group saw a possible engineered relic, some long-lasting device or probe, wrapped in a comet-like shell, built to endure star encounters just like the one we'd witnessed. The clash wasn't just about data, it was about what kind of universe we believe we live in. Is it a universe where we are still alone, listening only to rocks and ice, learning slowly from blind, natural wanderers? Or is it a universe where, every now and then, something passes through our neighborhood that was meant to be noticed, once our instruments became good enough to see it? For now, the official papers keep their language careful. They talk about non-gravitational accelerations, outgassing asymmetries, and constraints on nucleus properties. They describe 3I Atlas as a comet, an interstellar one, yes, but a comet nonetheless. Yet outside those pages, in documentaries, late-night conversations, and videos like the one you're making, the title hangs in the air like a challenge. New 3I Atlas discovery, why some astronomers think it might not be a comet. Not because we have proof of anything artificial. Not because the data force us to abandon the comet model. But because this object, this visitor from another star, sits right at the tension point between what we can explain and what we're still afraid to imagine. And as 3I Atlas glides quietly away into the dark, its faint jets fading, its radio whisper growing softer with distance, that tension remains. Natural ice ball or engineered relic, rugged survivor or deliberate messenger, we are left with the same unsettling, electrifying truth. For a brief moment in 2025, something from another star system cut through our sky, spoke in chemistry and light, contradicted some of our expectations, and then kept going. What we decide it was says as much about us as it does about the object itself. Before 3I Atlas, humanity's entire experience with interstellar visitors could fit on a single page. First came Oumuamua in 2017, an object so stretched, so oddly accelerated that even seasoned astronomers struggled to classify it. It had no visible coma, no obvious tail, and yet it moved as if something more than gravity were pushing on it. The debate over its nature never really ended, it just faded into speculation. Then in 2019 came 2I/Borisov. Where Oumuamua had been a riddle, Borisov felt like a sigh of relief. A classic-looking comet with all the familiar features, blazing coma, graceful tail, chemistry that lined up neatly with expectations. It was interstellar, yes, but also reassuringly normal, as if the universe were reminding us that not every visitor had to be strange. Seen against that backdrop, 3I Atlas doesn't fall cleanly into either category. It has the unmistakable signs of a comet, jets, water chemistry, a dusty halo, yet behaves in ways that twist the models just enough to be uncomfortable. It's as if Oumuamua and Borisov drew the two ends of a spectrum, and this newcomer chose to stand somewhere in the middle, refusing to let us close the book on either interpretation. That uneasy position raises the stakes far beyond a single object. If 3I Atlas is simply an unusually tough comet, then it tells us that other star systems can forge icy bodies with properties we haven't fully imagined. It hints at a galaxy rich with wandering debris, worlds flinging shards of themselves into deep space, some of which occasionally drift through our own backyard. That alone reshapes how we think about planetary systems and about the raw materials that might be seeding life across the stars. But if even a fraction of the doubts are justified, if any part of its behavior truly resists natural explanation, then the implications grow far more profound. An engineered relic surviving close passage by a star would suggest technology capable of enduring for millions, even billions of years. Its appearance in our sky would raise questions we are barely prepared to articulate: who sent it? Why this path, this timing, this disguise of ice and dust? And perhaps most unsettling of all, how many others have passed by unnoticed before our instruments were sharp enough to see? In that sense, the 3I Atlas debate is less about proving aliens and more about testing the limits of our imagination. Every time we push the data toward a natural explanation, we learn where our models are strong and where they bend. Every time someone suggests a more radical possibility, we are forced to confront how much of our certainty rests on habit, on the comforting assumption that the universe is indifferent. Eventually, 3I Atlas does what all such visitors must. Its jets weaken, its coma thins, and its brightness drops below the reach of smaller telescopes. Night by night, the images grow noisier, the signal fainter, until the object that once carried so many hopes and arguments becomes just another anonymous point sliding back into the starfield. Its trajectory carries it away from the sun, away from the orbits of the planets, and back into the long, cold corridor between stars. When the last useful observations are logged and the final models published, there is no single decisive headline. Most papers call it an interstellar comet because that is what the weight of the evidence supports. Yet almost all of them include caveats: uncertainties in jet strength, questions about internal structure, unexplained quirks in its behavior near perihelion. Officially, the mystery is constrained, not solved. Unofficially, it lingers. And that is where your story meets the viewer. Not at a neat answer, but at the edge of what we know, where a small, distant object has forced us to admit how much we still don't understand. Somewhere out there, 3I Atlas is already further from the sun than we will ever travel in our lifetimes, carrying its secrets in silence. We are left on a small world, under a familiar sky, replaying a brief moment when another star's wanderer passed through our light. Was it only a rugged shard of ice and stone, or a relic of intentions we have yet to recognize? For now, the only honest answer is this: it came, it puzzled us, and it left us with a question big enough to follow long after its faint glow disappeared from our telescopes.